Alright, today we're going to talk about exponential functions. So the first question is f of x an exponential function based on the chart? If so, write the function. Exponential makes sense in the sense that you're basically raising a number to a power. And every time it's going up by another power. So what you're looking for is if it's being multiplied by the same number each time. I always start here and figure out from 1 to 2, what did I multiply by? And sure enough, we multiplied by 2. To go from 2 to 4, we did multiply by 2. Go from 4 to 8, we also multiplied by 2. And I go from 1/2 to 1, we multiplied by 2. So therefore, we're multiplying by 2. Now, when we do that, that's saying it's 2 to a power. So the base number is 2, and we're saying it's to the x power. Which makes sense, because 2 to the 0, when I put a 0 in for x, you get 1. 2 to the first, you get 2. 2 to the second, you get 4, and 2 to the third, you get 8. So this would be my function. We look over here, we multiply by 5 to get to that one. We multiply by some fraction, what is it, 9/5? So right away, this is not an exponential function. So exponential functions come in the form of f of x is equal to some number to the x power, again, where n is a number. You're also going to see the number e, which is a number 2.7 decimal. It's basically a more common base that happens in exponential functions in the real world, so it's used a lot. So it's a base number that is common. And like I was saying, e is approximately 2.718 if you wanted to know what that number is. So a parent function sketch of a graph has a very common point. No matter what the base number is, if you raise that number to 0 when x is 0, you're always going to get the point 0, 1. So 0, 1 is a common point. You also always have a horizontal asymptote for the base one as 0, because there's no way to turn this into a 0 when you're raising it to a power. And then the sketch looks like this for the parent function. So you have 0, 1 as a point and the horizontal asymptote as y equals 0. We also have a domain of all real numbers, because x can be anything. And we have a range of y has to be greater than 0 because of that asymptote. So now we're going to try a couple of these. Now it doesn't matter what the base really is for these sketches. We just need to know it's always kind of that shape. So, so it says the parent function for this one is e to the x. So first let's list the transformations. The first one's happening up here with the x. So this is number 1, and then this is number 2. The first transformation is that we are reflecting with respect to, excuse me, and this is up with the x, it's not in front of the whole thing. So this is actually the y-axis one. Now we haven't done one of those in a while. And then number 2 is then shift the graph up 1. So let's think about what that does as my parent. My parent goes through the point 0, 1, and I'll do a dash for the parent just so you can see what happens. So this is the parent function. So now what we're doing with the parent function is we're reflecting it over the y-axis and shifting it up 1. Well, first of all, shifting it up 1 will now make the horizontal asymptote be up here, and this point is now at 0, 2. So my new point is at 0, 2, and we're reflected it over the y, so what it looks like is this. So the green one is now the new function. It reflected and moved up 1. My horizontal asymptote is now at y equals 1. My domain is always, for these functions, all real numbers. And the range, because it's at 1, we have to be bigger than 1. Over here, again, start with the horizontal stuff. That's step 1, which is shift right 3. And then we are 2 multiplying the y by 2. which is a stretch. That's what this one is here, the vertical stretch. So let's think about what that looks like. So the original, again, is at the point 0, 1, and it kind of looks like this. This is the original. So let's think of this point 0, 1. We're shifting it right 3. So 1, 2, 3, 1. So it's there. And then we're multiplying it by 2. So instead of being here, it's going to be up another 1 at 2. So this point is now at 3, 2. We are not moving the horizontal asymptote at all. That stays because we did not shift up anywhere. So this is the point. So it's kind of like this. It's still going to here, but it's going up faster. All right. That's how you kind of do the graphs. To solve exponential equations, here's the steps you have to do. You have to get the bases the same. Then you have to set the exponents equal. And then, of course, you need to solve for x. So get the bases the same, then set the exponents equal, and then solve for x. So let's do that. Again, you can always rewind and pause the screen if I'm going too fast for you. Alright, so example 3, solve for x. So this says 5 to the x. We need to figure out what 125 is. Well, if you use your calculator, you just know 5 times 5 is 25, times another 5 is 125. So it's 5 to the third. Now that these bases match, we can set the exponents equal. And since it's already solved for you, you're done. Next problem, 25 is 5 squared, and 125 is 5 cubed. Again, we have to find a common base. What happens here is power to a power, this becomes 5 to the 2x equals 5 to the third. Now that the bases match, we can set the exponents equal. 2x equals 3. Now you have to solve for x, so we get x is equal to 3 halves, or you could tell me 1.5. Alright? So the key is figuring out how to get these to match. 3 is already a base number that's low. But we have to think about what is 27. So we have 1 over, 27 is 3 to the third, because 3 times 3 is 9, times 3 is 27. However, that's on the bottom. So you have to remember your exponent properties. When you have something on the bottom and you want it to be on top, you have to make it a negative exponent. So this becomes 3 to the negative third. Now these match, so we can set the powers equal, and I get x is equal to negative 3. So again, we brought the 3 up, they match, set them equal, good to go. Alright, with big numbers like this, you can kind of figure it out, but generally if it's even, it's probably going to be a base 2. And I believe this is 2 to the 7th. And you can check on your calculator if you needed just 2 to the 6th, 2 to the 7th, 2 to the 8th. 2 to the 4th would be this one. So what you have to do is multiply these together. So you end up with 2 to the 7x is equal to 2 to the 8x plus 8. You have to distribute that 4. Now that our bases match, we can set the exponents equal. Final step, let's solve for x. Move the negative 8 over, so we get negative x is equal to 8. Divide by negative 1, x equals negative 8. And there we go. That's those. I think we got 2 more. All I'm doing here is changing the base on you. E is already the common base. E is the common base. Let's just simplify the powers. E to the 4x. Okay. Now that I have a base equal to a base, I set the power equal to the power. Move the 2x over. Divide by 2, you get x is equal to negative 1 over 2. Now this one's a little trickier because we have 2 bases on the same side. They match, but you can't just say it's x times x plus 3 equal 4. When you multiply bases together, you end up adding the powers together. So this ends up being e to the x plus 3. Remember, that's a power. If you multiply bases, you add the exponents. Now we can simplify. That becomes x e to the 2x plus 3. That becomes e to the 4th. You could set the exponents equal, and we can now solve. So if we move this over, we get 2x equals 1, x equals 1/2, positive 1/2. Okay, so that is how you solve exponential equations. You have to get the bases equal, one base on each side. Then when that happens, you set the exponents equal and solve for x. All right, tomorrow we will start with logarithms.